This says we have a 2 kilogram block is released from rest at the top of a curved incline in the shape of a quarter circle of radius r. The block then slides onto a horizontal plane where it finally comes to rest 8 meters from the beginning of the plane. So that's indicated right here. The curved incline is frictionless, but there's a coefficient of friction of mu equals 0.48 while the block slides horizontally. So only in this rough portion here, indicated by the dashed lines, is there that friction. So what is the work done on the block in those 8 meters? So to begin this, we know that work is equal to force times distance times the cosine of the angle between those two vectors. Now, what's the force that we're talking about here? That force is the force of friction there. And what's the force of friction equal to? Mu times the normal force. And if we're on a horizontal surface like this, the normal force is equal to the weight, so we can say mu mg. So let's plug all of that into here. We get mu times m times g times distance times the cosine of the angle between the two. And now let's start to plug in some numbers. So mu is 0.48, mass is 2 kilograms, g is 10 meters per second squared here on Earth. The distance is 8 meters, and the cosine of the angle between the two is 180 degrees, because it will slide this way, but the force of friction will be back that way. If you put all those into your calculator and get a number, you should get the work is equal to negative 76.8 joules. It makes sense that it's negative because we took away the energy from that block because we slowed it down there. So the next question says, what is the speed of the block at the beginning of the 8 meters? So remember to start this one off that the work is also equal to the change in kinetic energy. So we can figure out how much its kinetic energy changed because we already know its work. So we actually already know that. It drops 76.8 joules of kinetic energy. And since we came to a rest, we can say, well, that means that initially it must have had 76.8 joules of energy. So we can just set that equal to 1/2 mv squared and solve for our velocity. So 76.8 joules is equal to 1/2. The mass is 2 kilograms. Solve for v. If you plug that into your calculator and work it all out, you should get about 8.76 around there meters per second. These two, between part A and part B, they often cause confusion, and sometimes people try and solve a problem where you need to do it by change in kinetic energy when you they'll try to it'll need to be solved that way and they'll try to force it this way, or it'll need to be solved this way and they try to force it that way. So how can you tell the difference? Well, it's by what they gave you. If they gave you any sort of thing like coefficient to get the force and the distance, you're going to solve it this way. If they told you something about the speeds, then you're going to do it this way. So the next one says calculate the radius of the incline here. So what we need to realize here is that we are doing a conservation of energy problem, because up here we had gravitational potential energy and down here it converted into kinetic. So we can say that our gravitational potential energy became the kinetic energy. Well, we actually already found that kinetic energy. Remember? It's 76.8 joules. It's equal to our change in kinetic energy. It's equal to our work. So we can just go ahead and say our gravitational potential energy is 76.8 joules. And then we can set that equal to mass times gravity times height. So we can say 76.8 joules is equal to a mass of 2 kilograms times gravity, which is 10 meters per second squared, and solve for the height. And if you do that, you wind up getting 3.84 meters there. So last part is it says if the mass of the block was increased to 4 kilograms, so we doubled it, how would that affect the distance that it slides? So you may have an intuitive guess by now that it's going to be equal, but let's show why it is equal. First thing is the gravitational potential energy to the kinetic. Well, that's mass times gravity times height, and it goes into kinetic, which is 1/2 times mass times velocity squared. So the masses cancel out, and if you are a height of r above the surface here, you'll always be going the same speed no matter what. Now, the second part. Well, we got to take away all of that kinetic energy. And that's got to be done through work. And that's got to be done by a force of friction times the distance. So here we have 1/2 times mass times velocity squared for our energy. And over here, the force of friction, as we discussed, will be mu times the normal force. But the normal force will be equal to the weight on a flat surface like that. So once again, the masses cancel, and you would have more kinetic energy to begin with if you had more mass, but you will have more force of friction in order to slow it down.